This video is going to be about a brand new vector math operation. It's called the cross product. This is kind of one of the last pieces of the puzzle in the foundation of vector math. And I'll be honest with you, this one is a little bit more complicated, so you should take it very slowly. We're going to work through a couple of examples, but pause the video as you need to, rewind and rewatch stuff. It can be a little complicated, especially the first time you see this. So I'll try to go slow, but use the video to your advantage and pause it and go back anytime things don't click right away. So the definition of the cross product is that it's a vector math operation that takes two vectors, it crosses them, and the result is a new vector that is perpendicular to both of the vectors that were in the cross product. So in this case, I have A cross B. So vector A crossed with vector B. And the results I'm calling vector C. So notice that the cross product takes two vectors, it crosses them, and it returns a new vector. And the special thing about that new vector is that it is perpendicular to both of the vectors that were in the cross product. The only way to generate a new vector that's perpendicular to both of these vectors is it was pointing in a new dimension. So there's a plane that is defined by the original two vectors that are in the cross product. So if you can kind of imagine connecting these vectors and creating a plane, like a surface, the new vector, vector C, that's the result of the cross product, is perpendicular to that plane. All right, and we're going to use that fact to our advantage in order to describe and to use these cross products. So I just want to be really careful here, and when you are doing problems involving cross products, be very careful that you are drawing that X or that cross, and you are saying cross, like vector A crossed with vector B, so that you are not confusing the dot product with the cross product. These are two completely different vector operations. You should never say a vector times another vector. That operation doesn't exist in vector math. That's scalar math. That's the math you've been doing your whole life. You must be very specific when you are talking about some kind of vector multiplication. You need to say the dot product if you are referring to the dot product. Or you need to say the cross product when you are referring to a cross product. Be very careful because these operations are completely different. So I want to give you a little bit of intuition about what the cross product really does. So I kind of showed you a little bit there that when you cross two vectors, let's say vector A and vector B, they form an area, or they form a surface. And so this area that they span, that's a word or a vocabulary that you might hear, this surface area that they create, that area, the magnitude of that area corresponds to the magnitude of the cross product. And the direction of the cross product is perpendicular to that area. So vector A and vector B must span an area. So there has to be some angle between vector A and vector B. And by doing that, you can kind of create this area just by connecting the vectors and connecting the lines and forming an area. If vector A and vector B cannot form an area, if there's no angle between vector A and vector B, then their cross product is zero. It can't create a cross product. So that's the physical interpretation of what the cross product is actually doing. That's what this new vector represents. It's a new vector whose magnitude represents the area spanned between the two vectors in the cross product. And the direction of this new vector is perpendicular to the area spanned by the two vectors in the cross product. So always come back to this picture and remind yourself kind of the directions and why the vector is pointing in a certain direction or another. So to actually perform a cross product, you can do it in a couple of different ways. The first method I'm going to show you is the graphical method. So this is like drawing arrows, looking at vectors, is a picture, and figuring out the cross product in that way. So to do it in the graphical method, there are a couple steps here. Step number one is first we're going to figure out the magnitude of the result of the cross product. So let's say we're crossing vectors A and B. First thing you want to do is figure out the magnitude of the result of that cross product. So it's defined as vector A crossed with vector B. The magnitude of that cross product is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. And that angle, this is very specific. You must define this angle, very similar to how we've been doing it already. And that angle theta is the smallest angle between vectors A and B when they are drawn tail to tail. Make sure you're drawing your vectors tail to tail when you are doing cross products. Cross products and dot products, your vectors should be tail to tail. All right, so that's how you figure out the magnitude of the cross product, or the norm of the cross product. You just need the norms of the two vectors that are in the cross product and the angle between them when they are drawn tail to tail. That gives you the magnitude. That's just one piece of the puzzle. The next thing you need to do is find the direction of the cross product. The direction of the cross product is determined by the right-hand rule. You've already had an introduction to the right-hand rule when we were talking about the Cartesian coordinate system. Now we're going to generalize it to any cross product ever. So this is how you would do the right-hand rule for any cross product. You want to make that shape with your right hand where you make an L with your pointer finger and your thumb, and then you point your middle finger perpendicularly outwards, like from your palm. Okay, so that's the shape you want to make. And now you want to make the following assignments to your hand. So your thumb represents the first vector in the cross product. So in this example of A crossed with B, your thumb represents vector A. Your pointer finger represents the next vector in the cross product. So in this example, your pointer finger would be vector B. The angle between your thumb and your pointer finger, you notice that you have an opposable thumb, and so you can move your thumb relative to your pointer finger. So you do not have to maintain a 90-degree angle here. If your thumb is vector A and your pointer finger is vector B, then the angle between your pointer finger and your thumb should represent the angle between those two vectors. So sometimes it's 90 degrees, sometimes it's less than that, sometimes it's greater than that. Personally, my thumb doesn't go greater than 90 degrees, but technically it could if you could kind of like pull it out of the joint and do that. But that's what you should do. Just create that shape and try to make the angle as close as possible to that actual angle theta that's between vector A and vector B. All right, and now your middle finger describes the result of the cross product. Your middle finger has to be perpendicular to your palm, because your palm represents that area, that surface area between vectors A and B. So it is very important that you do maintain a 90-degree angle between your middle finger and your palm. All right, but that's how you determine the direction of the vectors in, or the result of the cross product. So let's do an example. So let's say we're figuring out this cross product. A crossed with B results in vector C. Reminding you again, these are the assignments to your hand. Let's do example number 1. So vector A is your thumb. And in this example, vector A is pointing into the board. That symbol means into the board. So your thumb is going into the board. Your pointer finger is vector B. So your pointer finger should be going to the left. So if my thumb is going into the board, my pointer finger is going to the left, my middle finger is pointing straight up. So I would say vector C, the result of that cross product would be pointing straight up. Let's try another one. So example 2. Now vector B, that's the second vector in the cross product, that is your pointer finger, is coming out of the board. That symbol of the little dot means out of the board. Okay, so your pointer finger is coming out of the board, like imagine it coming out of your computer screen. You can see the tip of your pointer finger. And now the result of the cross product is pointing upwards. So in order to do that, now my middle finger is pointing up, my pointer finger is coming at my face, my thumb is pointing to the left. So that means vector A must be going to the left for this cross product. To generate that cross product, A must have been going to the left, B is coming out of the board, my middle finger is pointing up. All right, let's try one more. You should pause the video and try to do this one on your own and check your answer. So this third example here, all right, vector A, that's my thumb, is kind of going like up and to the left. Remember that A and B do not have to be 90 degrees to each other. So right now, try to make your thumb go kind of up and to the left. Vector B, that's your pointer finger, is pointing to the left. And now describe the direction of your pointer, or sorry, your middle finger. My middle finger is pointing out straight at me. I can see the tip of my middle finger. So that means that vector C must be coming out of the board. All right, so redo those. If you weren't getting those every single time, go back and redo them and convince yourself of those answers. All right, so we kind of talked about the magnitude, the direction. Let's do an example where we do all of this stuff together. So I have two vectors, M and P. I know the norm of vector M is 25 newtons. Vector P, both of these vectors M and P live in the plane of the board. Vector P has a magnitude of 10 meters. So we can see how they're pointing there. We want to figure out the magnitude and direction of T. Notice this definition here, that T is the result of M cross P. So we can figure out, use the right-hand rule to get the directions. We'll use that definition of the cross product to get the magnitude, and to put all this together, we're going to find vector T. So let's first find the magnitude of T. So the norm of vector T is going to be the norm of M crossed with P. So that would be the norm of vector M times the norm of vector P times the sine of the angle between them, but we need to draw them tail to tail. So I'm going to draw vector P up here again. Here's vector P. And I know that vector P makes this angle right here, that's 30 degrees with that horizontal line. So to identify the angle between them, that will be this angle right here. I know a straight line makes 180 degrees, and so I know 40 is over here, 30 is over here. So this angle theta must be 180 degrees minus 40 minus 30. And that is 110 degrees. So angle theta is 110 degrees in this problem. All right, so now let's just plug in all those numbers, and that'll give us the magnitude of the cross product. So that'll be 25 newtons times 10 meters times the sine of 110 degrees. And I get 234.9. And the units, I see newtons times meters, so my units are newtons times meters. Okay, that is the magnitude of vector T. So we only got one piece of the puzzle. We still need the direction of vector T. So let's use our right-hand rule to figure out the direction of vector T. So the cross product is M crossed with P. So vector M is your thumb. Vector P is your pointer finger. And vector T will be your middle finger. So try to do this right-hand rule with your thumb, or with your with these vectors here. So M is kind of pointing, let's see, down and to the left. P is pointing down and to the right. So if you can kind of like, if you're looking at your computer screen, like really do that, put your hand there and make your thumb go down and to the left. Your pointer finger is going down and to the right. My middle finger, I can see the tip of my middle finger. It's coming out at me. So that means that vector T is coming out of the board. So now putting those two things together, vector T points out of the board with a magnitude of 234.9 Newton meters. That is vector T. We have a magnitude and a direction, we're done. What if I had asked you this problem instead? Can we solve this problem a little bit faster now that we know we've already done the previous one? Now we have the same vectors, M and P, same magnitudes, 25 newtons, 10 meters. They have the same directions as in the previous problem. This time, we want to talk about vector S. Vector S is P crossed with M. So it's slightly different. Remember that vector T was M crossed with P. How is vector S going to be different than vector T? Well, let's try it again. Let's do the magnitude of vector S. It would just be the norm of vector P times the norm of vector m times the sine of the angle between them. All of those things are still the same. I didn't change any of the angles. I didn't change any of the norms. And so the magnitude of vector s should be the same, 234.9 Newton meters, because theta is still 110 degrees. That stayed the same as in the previous problem. So far vector s has the same magnitude as vector t. Let's talk about the direction this time. This time vector s is defined as p crossed with m. So in this case, vector p is going to be your thumb, and vector m is going to be your pointer finger. So now let's figure out the direction of vector s. That'll be your middle finger. So now do it this time. P is your thumb. So this one hurts my hand, but I can do it. Point your thumb down and to the right. Point your pointer finger in the direction of M. That's kind of down and to the left. This one's tough to do, but if you stand up, you can do it a little bit better. So my thumb is pointing down and to the right. My pointer finger is going down and to the left. This time, you guys can see the tip of my middle finger. It's going into the board. So this time, vector S is going into the board, which is the exact opposite of what we got in the previous problem. T was going out of the board. S is going into the board. So notice what changed. We inverted the order of M and P between these two. We inverted the order of the vectors in the cross product. And notice that the magnitude of the result didn't change, but the direction changed. So what I want you to notice here is that a couple properties of the cross product that are very important for you to remember is that the cross product is anti-commutative. This is a very big fancy word that basically says that if you invert the order of the vectors in the cross product, you pick up a negative sign. So A crossed with B is equal to negative B crossed with A. So you can use that to your advantage. If you already know what B crossed with A is, then you can very quickly get A crossed with B. It's just the opposite sign. So be very careful with your order. Another property of the cross product that you want to remember, it's distributive. So you can, if you had A crossed with B plus C, then that's the same as like A crossed with B plus A crossed with C. Just again, be very careful with your order that it's A crossed with each of one of those. So A is still the first vector in each of those cross products. The other property that you should remember, this will help you out and kind of give you a shortcut. Any vector crossed with itself is 0. Remember when we talked about a vector, the two vectors in the cross product spanning an area? If the vector is with itself, if this is vector A and this is vector A, you cannot form an area with a vector if there's no angle between it. So vector A crossed with vector A is going to give you a 0. Also, if your two vectors have 180 degrees between them, again, you cannot draw an area. I can't like form this into an area. So also the cross product of anti-parallel vectors is also going to be 0. And you can get that right out of the definition of the cross product, because if you do the sine of 0 or the sine of 180, you'll get a 0. So it will come out in the math. If you can't remember this, it will come out in the math. All right, so that is your first introduction to the cross product, is doing things graphically with these definitions. So we'll stop there for now, and we'll do the cross product in another way in the next video.